So to continue with this zero ion, so the Pi, the isoelectric point, is at some pH, which varies from amino acid to amino acid, at which the concentration of this form is at maximum. All right, so you could kind of see what happens to this zero ion depending on whether or not it's sitting in a more acidic pH. So what you're shown here to the left is that if you decrease the pH from this Pi, from this neutral species, okay, so think of this species, all right, so think of yourself as having two functional groups. One is the ammonium ion plus, and then you have a carboxylic ion. Those are the two functional groups that are present. And if you're sitting in acidic media, by decreasing the pH from its Pi, then it's going to get protonated. Where is it going to get protonated? Not on the amine, because it's already got the plus charge. Where it's going to go is at the carboxylic acid salt. It's going to go grab the proton, so now it's going to be attached to the carboxylic acid salt. So notice that overall this species is going to be in a cationic form or plus charge, and that's the form that's going to dominate in a lower than Pi pH, or more acidic than its Pi, right? So the flip side of that, that's why this is amphoteric. It acts like an acid or a base, depending on what environment is in. All right. So now instead of sitting in a more acidic media, let's pretend that it's sitting in the more basic media, where there are more hydroxide ions. Then what's going to happen is that from this neutral species, this proton right here is the acidic proton, right? I mean, the carboxylic acid is in a salt form, and there aren't any other acidic protons. So that's going to get deprotonated by this base because it's sitting in the basic media. And it's going to, the ammonium ion is going to become amine. So then that means the overall, this is going to be a negatively charged species, anionic form, and that's what's going to be dominating at a strongly basic solution. So depending on its the pH of the environment and comparing that to the Pi, you'll see a titration curve like this. This is showing the change in pH as more and more equivalents of hydroxide ion is added, and this just graphically describes exactly what we talked about in the equation form, in which the from the Pi, where is a neutral form, if you go more and more acidic, you are going to have this form dominating, where the carboxylic acid salt is going to get protonated. From here, if you go more and more basic, then it's going to grab that extra proton off of ammonium ion, and then so overall it's going to be negatively charged, and this is the form that's going to dominate. All right. So I think before we go and look at the different scenarios depending on what amino acids you have, let's look at the acid-base properties of amino acid and compare the pKa of the amino acid. So let's compare just normal acetic acid versus the acid on amino acid. All right. So you would think the pKa should be pretty similar for the carboxylic acid that we're looking at, but the acetic acid pKa is around 4.6. Whereas the carboxylic acid from the amino acid is around 2.3 for most, if you look at their table in the book. And so the question is then, why is this proton, even though it's a carboxylic acid, Same as here, carboxylic acid. Why is this proton more acidic than this proton, even though they're both carboxylic acid? And what you have to look at is the influence of the ammonium group that's having on the carboxylic acid. So the ammonium ion is acting like an electron withdrawing group because of the plus charge. So inductively it's pulling electron density towards it, causing this proton to be even more acidic. All right, and that's why the pK is lower. All right, and flip side of that is if we look at just a regular amine versus the amine of the amino acid, okay, so we're looking at this form now, right? So if you look at the basicity of these two, the pKa of the regular amine is 10.6, whereas this amine is 9.69. So what is that telling us? That the regular amine is more basic with the higher pKa than the amine that's in the amino acid. Once again, this carboxylate ion is acting like an electron withdrawing group, pulling the electron density inductively towards it. So that's why this lone pair is not as basic as the one that does not have a carboxylic acid salt next to it. All right. So keep that in mind. These trends as we look at different amino acids. All right. So what I have here is I summarized what would happen depending on whether your side chains are neutral or acidic or basic, what form is it going to be in, and what overall charge it's going to have. All right. So when R is neutral, when the side chains are neutral, and this applies to about 15 amino acids, so we are talking about all of the non-polar amino acids as well as polar neutral amino acids when we talk about this. And if you look at the PI values for these two groups, they don't really change that much. It's between 5 to 6.5. All right. And by and large, it will be in the form that we discussed up here, where, so it's a simple scenario where whatever PI you have, you're going to have a neutral species. And then if you're in a more acidic, so if you're in a more acidic environment, like if the PI of this was 5, and if you are in an environment that's less than 5, then more and more of this form will dominate. And then if the environment that you're sitting in is greater than its PI, then more and more of this form will exist. And simple as that, that's it. Okay, the complication occurs when the side chain also have an additional acidic or additional basic group. So let's look at the glutamic and aspartic acid. And this applies to the 2 amino acids that are acidic. And the PIs of these two are around 3. So that means this is the zero ion, the neutral species, and notice the plus and the minus. And notice that this carboxylic acid, in order for it to be neutral, is still in a protonated form. And that's why the PI is so low, because if it wasn't a higher PI, this would already be deprotonated, right? So if it was less than 3, what will happen then is, since this is already protonated and this is plus charge, the only place the proton H plus could go is in here. So then you have this form, and the overall charge for this is a +1 charge, right? And the reason why I talk about the overall charge is because that has impact on electrophoresis, which is what we're going to talk about in a bit. All right. So Now we're gonna switch gear and say, let's say this aspartic acid is in pH that is greater than 3. So as slowly as you titrate it, what will happen is, because it's in a more basic environment, this proton is going to be more acidic than this proton, correct? Because this is like pK of 4-ish, and this is pK of like 10, right? 9 or 10. So this is going to get deprotonated first, as you might expect. So then the overall charge is -1. But if you keep adding base and you make it more and more basic, eventually, after all the proton has been deprotonated, it's going to go grab this proton, which is the next acidic proton that's present. And if you get to be really high in pH, then it's going to have an overall -2 charge. And that's the form it's going to be in, right? Now for amino acids that are basic, which there are 3 amino acids that are in this category. And the pI for this, as you might expect, is between 9 and 10. All right? And that should make sense because these have extra amine groups on them. So it has to be pretty high in order to keep this in a neutral form. So notice the neutral form, you have the negative and the plus, but unlike the neutral form over here where the amine of the amino acid is protonated, here we talked about the amine, regular amine, being more basic than the amine from the amino acid. So you see that the at the pI, this is the one that's going to get the proton first before this. So this would be the neutral species. And if you take this and put it in a more basic environment, then it's going to grab that proton. So then it's going to be overall -1 at greater than 9 pH. But then if you went the other way and put it in a more acidic environment, then what's going to happen is it's going to get protonated. And of the 2 sites that could get protonated, obviously this is more basic than the carboxylic acid salt. So notice pH less than 9, it's going to be protonated over here. So the overall is +1. And then if you keep going and making it more and more and more acidic, like pH of 3, in that environment, it's going to keep getting protonated such that even the last site is going to get protonated. So overall, this is going to be +2 charged. All right. So at this point, you should be able to do these problems, 25.1 through 25.5 and 25.10. And I will continue finishing this lecture on the next lecture.